Okay, once again, briefly, I count this as a row, this, right? And I count this as a row. Now, for this row, these are the flips that Joanne did, right? And these are the flips that Corbin did, and so forth, okay? Now, I did my coins in a row. I scrambled them and laid them down in a row of 7, okay? So the first time, this is my first, second, third, fourth, fifth, sixth, seventh coin. That's how I did mine. Because I had to flip a bunch of them to match the one flip everybody here did, right? So we see that counting 5 flip rows, okay, my first coin, my second coin, my third coin, down through my 7th coin, as it came up in 5 different tries, and your 5 different flips, okay, Jones and Corbin's and so forth, okay?
Yeah, Jones.
Got it? Joanne, sorry.
No, you're good.
Yeah, Jones.
Yeah, a family I spent a lot of time with, had a guys my age, month different, and there were 7 kids in that family. And they had, the mother was Joanne, and the daughter was Joni.
That's
Okay?
My
not
grandmother's name is Joan.
So right now I'm messed up on those names, so I do apologize.
I don't mind. Okay.
Ingrained deep in my brain from my childhood. They had the neatest house I ever saw. Okay. So what we found is on the 5 flip rows, no row had 5 tails, no row had 4 tails, 5 rows had 3 tails, 7 rows had 2 tails, 1 row had 1 tail, and no row was lacking tails. So I can do this. I can make a bar graph, and you all know how to do this. So I can have 0, 1, 2, 3, 4, 5. Okay. For 3 tails, I got 5, so I'm going to have a bar here that's 5 units high. It's not a trapezoidal graph. I'm just going to put the 5 in there to indicate it. For 2 tails, I had 7. And for 1 tail, I had 2. That distribution kind of makes sense. It appears to be more likely that I'll get 2 or 3 tails than I'll get 1 or 4 tails, right? Also, you would expect that if we did this a large number of times, I'd get 2 tails about as often as I get 3 tails, if it's a fair coin, okay? Because if I get 2 tails, that means I get 3 heads. And if I get 3 tails, I get 2 heads. And if 2 tails is as likely as 2 heads, and 3 tails is as likely as 3 heads, then these numbers ought to be the same. Since it's a fair coin, these numbers should be the same, with a large number. Now with a smaller number, you know, total a sample of 14, it's certainly possible that things are going to be off a little bit, okay? Maybe the ideal distribution is 1, 6, 6, 1. And it's unusual to get 5 heads in a row or 5 tails in a row. So on a 14, sample of 14, maybe on the average don't expect to get any of these. On a sample of 1,024, maybe you would expect to get a lot of them. But still, you're going to get more of these than you get these, okay? Now, the distribution for 4 flips, and to do 4 flips, what I did is I just cut this part of the distribution off and I counted the columns. That distribution came out like this. Okay? So for 5 flips, there's our distribution. For 4 flips, we'd have 0, 1, 2, 3, 4.
Okay, for 4 flips, you flip it 4 times and
Yeah.
what?
Well, I just counted the first 4 flips in each column. There are 10 columns, so I got 10 results. Okay? Now this one turned out to be more symmetric than you would expect for a small number of flips. 2 tails occurred 5 times. 1 tail occurred twice. No tails occurred once. And 3 tails occurred twice, and no tails occurred once. So we have this perfectly symmetric distribution, which is what you really expect. If you do a large enough number of coins, it's going to be close to being symmetric. Okay? That make sense? Actually, I've given you a symmetry argument when I said that if it's a fair coin, you would expect the same distribution for the number of heads as you would get for the number of tails, which is exactly what makes it symmetric, and you might have to think through that. It's the kind of question I'd ask you to analyze a little more, maybe on a final, take-home final, where you can think about it over a period of 7 days. Okay? Okay. So, and that fits into what I was saying about the process of solving challenging mathematics problems. You think about them as much as possible right away. You try to get the problem in your head, and you try to get them all in your head. Then you come back to them the next day. And I mean, if you get a good idea immediately, or some idea of how to approach the problem, you make yourself a little note so you don't forget. Okay? Especially if you're my age, when you don't have any working memory and forget what you just said 2 words ago. Okay? You got to be careful to write down your thoughts and learn how to assemble them, right? But even at your age, where your memory is in not quite optimal shape, but it will be within the next decade, okay? Then it'll start trailing off. But your experience grows, so your ability grows for a couple of decades, and depending on your field, maybe for your whole life. So what you do is you prepare yourself. Every day you think about every problem. You make yourself little notes on it. For the first couple days, you just assemble your notes. Although some problems you say, yeah, I'm not going to be able to solve this, but right now I'm going to think about the ones I'm not sure about. That makes sense? And you spread it out. Now, some of those days we're going to be traveling, we're going to have other activities, so you kind of think about, when am I going to have time? And you're not going to have to be here on that second to the last day, on that Thursday. We're going to get in the wee hours of the morning. You want to be sure you get enough sleep so you can assemble your problems, right? Now, we'll make the bus really boring, so you get some sleep on the bus. But you want to balance out your time. You want to plan out how you're going to approach this thing. Okay? I'll probably put a rating on each problem too. I'll go 0 to 50.
Yep.
But 50 doesn't mean nobody's ever solved it.
I would, so this
50
is
means that's about as hard a problem. I don't expect anybody to completely solve it. And if you do, that's really good. Somebody always surprises me in one way or another.
Do you average the take-home exam or the in-class exam?
The what?
Do you average the take-home exam?
I'll tell you how that works out when I decide.
Whatever is the highest one should be the one you take as our final grade.
Yeah, well, the other thing is, if you come in and can't do something on the exam in class that you did perfectly on the take-home, that's going to work against you.
What do you mean?
Because that means you probably used somebody else's solution. Okay? So there's going to be some interplay. Doesn't mean you can't talk about it. But if you copy down somebody else's solution, or I see evidence of plagiarism, I mean, if you discuss the thing, of course different people are going to have different problems, different numbers and stuff, but if you discuss the thing, that's fine. If it's not really your solution, I'll be able to spot it, and that's going to work against you, right? Don't be paranoid about it, just don't do it. Okay?
Well, we can talk about the function or what we go through to get your answer, right?
Yeah, you can talk about the process, you can talk about the concepts, you can talk about what the words mean, talk about how to interpret it, okay? I want you to work together, okay? Okay, and I know you will, because that's all, you know, you're doing a lot of that to start with, especially when I ask you to, but then you get these great discussions at breaks and at lunch, you know. So, you know, y'all are interacting in a way that is best if it arises spontaneously, which it did almost instantly with this group, instead of me trying to encourage it, which doesn't work as well. If I try to encourage it, I'm the enemy, you know. Nobody in their right mind is going to do what I want them to do. Okay. In other words, y'all have emerged in a really, really good group. And I saw that almost immediately. And I want you to continue that, but I don't want you to represent work on your take-home exam that isn't really yours.
Yeah.
It's got to really be, when you sit down to write it, you got to sit down to write your own work. And if you mess parts of it up, well, they're going to be hard problems. I don't expect miracles. I expect good attempts. And then if you present something that as your work and then show me on Friday morning that you didn't know it, well, I'm going to reduce the credit I gave you on that part of your take-home.
So-
Or actually, I'll probably be looking at them both simultaneously.
So
And
it'll
it's not
help
going to
us.
be all the same problems, but I'm going to have enough problems that are similar to what the take-home is that, you know, when I grade them, I've got to consider all that. Okay?
So in other words, our take-home exam could help our grade for our final exam
Yeah,
here,
Yeah.
even though you ain't grading it like that.
yeah. So I can't give you a formula for how it's graded because it's way too complex.
Way too complex.
We're not on his
You
level.
just trust me
Ron.
to
We
give you
trust
the best grade I can justify, and to compare grades, and to compare work, to compare the, you know, whole portfolio of your work with what everybody else did, and if somebody else got a higher grade for work that looks about as good, you're going to get the higher grade. Okay? Okay. Okay, so, again, this distribution is symmetric. Now, the big deal is that you've got a color that contrasts. Where is all my, and I can never find the color I'm looking for. Well, this is important. This is red. Are you ready? This could well be not a trapezoidal approximation, but this could well be a bunch of trapezoids that have been converted to rectangles that represent a curve that looks a whole lot like this,
That's pretty cool.
right? That makes sense? Now this one doesn't look quite as good, but if you adjust it a little bit, it works. This one looks really bad, so, you know, we don't always get a good distribution. I'm going to ask you to do histograms like this based on different ways of counting these,
Jeez, man.
okay? Like, maybe I say, go down the diagonal here, okay? Or something like that. Probably won't say that. Maybe I say just count the first 5 in the column and see if the distribution is like the one I got here, or how it differs, okay? Or count the first 6 in the column. Doesn't take long. You can spot it pretty quickly, okay? Make sense? Okay? And then we take those numbers and we can compare with the normal distribution. Now what the normal distribution is, let's say this was a big conference hall and there were 1,000 of us, and everybody flipped their coin 1,000 times and we calculated everything. So we'd have 1,000 instances of 1,000 flips, right? Make it 1,024 instances of 1,000 flips. 1,024 being a power of 2. It's easy to calculate
1,024 power of 2.
the number of ways you could get each result. And we're actually going to talk about that, but yeah, probably tomorrow. Okay? It's real easy to calculate. Matter of fact, I know my grandson saw it in 6th grade. Combinations and permutations. Anybody, those words ring a
I
bell?
didn't see those in 6th grade, I saw those in Algebra 2.
Huh?
I didn't see those in 6th grade, I saw them in Algebra 2.
Yeah. Well, he saw them in 6th grade and didn't remember them. So it's probably too early to see them. So if you didn't see them in 6th grade, I'm not going to throw stones at the curriculum for that. Okay? So that might have been overreached. You know, maybe 11 and 12-year-olds, 10, 11, I don't know what age is 6th grade anymore. Yeah, I think it averages kind of 11, at least some part of the year. Maybe that's too young to talk about that. Or maybe maybe it isn't, maybe they just didn't spend enough time emphasizing or didn't test on it or something. I don't know. Anything is possible. Now, my point is, if you have 1,000 flips, what's the picture going to look like? Well, I'll tell you what the picture looks like. It pretty much looks like this, which is a perfect normal curve. And of course, you know, you've got to divide this up into a lot of histograms, right? Good thing I'm so quick. Okay? And the histogram pretty much melts into 0 by the time you get down to, like, I'm sure by 35 or 65. It's very rare that you would get only 35. That's on 100. Okay, on 1,000. I could calculate it. We calculate the standard deviation. Actually, it's p times 1 minus p times the square root of n. So it's 30 times 1/4. So it's 8. The standard deviation is 8. So you go over 2 standard deviations. That's 16. And if I calculated that right, you're pretty much down to 0 by the time you're over here at 500 and okay, 24, 500, 476, and 524. So you've only got like 48 bars that are even visible because the rest of them are too tiny. And maybe a few more of them will be visible. Maybe it goes to 450 and 550, but it doesn't go much further than that. Okay? Now I'll explain that calculation I did because we can actually develop it if we have time. The point is that the normal distribution tells you that the expected number of heads or tails is the most likely, but the ones right next to it are more or less equally likely if you have a lot of heads. Okay? But then it drops off pretty quickly. Now for just 4 flips, what is it? Well, you all have seen Pascal's triangle, haven't you? Have you? Okay. Well, there's another digression. There are a couple of books that I'm going to recommend that you get because they only cost a few bucks online, used copies. And there's one, it's just a basic sub-pre-calculus level math text that has more advanced math in it than you'll ever see in pre-calculus or calculus. It has this stuff in it. It has some pretty good probability and statistics in it, and it'll be good for you to know. And you can pretty much work through it recreationally. People that don't qualify for pre-calculus can often just sit down and work through the problems with no problem. Okay?
They're that easy.
Yeah. And it takes about an hour a section. Now there's some challenging problems in there, but it's excellent stuff. And as I say, you get more fields of higher mathematics than you'll ever see if you don't. Okay? And you can it's all stuff you can use if you take a lot of math in college.